Hi everyone, welcome to the last lecture of CS330. Today it's a very exciting lecture. We'll be talking about frontiers and open challenges in multitask and meta learning. And we'll have 8 speakers who will tell us about some of their work that is at the frontier of multitask, meta learning, and actually other subfields as well. So it should be really exciting. It would give you the opportunity not only to learn about their work, but also to actually meet the people who are behind it. Before we get started, a few logistics. So again, this is the last lecture today. We will have the instructor office hours right after this, which will be also held on Zoom, and the link to join that is on Canvas. And then on Tuesday, we'll have the project poster session, and on Wednesday, the projects are due. One more thing is that we'll have the final course survey at some point. I'm not exactly sure when you will get an email about this, but you will. And we really appreciate your feedback. That really helps us improve the course, and we incorporated a lot of the feedback from previous years to make the course better. So please take the time to fill those out. These are really, really helpful, and we really appreciate your feedback. All right, so today we'll be talking about frontiers and open challenges. And I split them into 2 big topics. One will be about utilizing zero-shot generalization of large language models. And we talked quite a bit about large language models. We had one of the lectures on it, one of the guest lectures from Colin on it. And we'll explore some of the questions when it comes to using these large language models. We'll talk about how to fine-tune these large models without negative transfer. And we'll also talk about how we can apply these large language models to other domains, such as robotics, for instance. And then in the second part of the lecture, we'll talk about how we can make reinforcement learning a better data sponge. And this might be a little enigmatic at this point. I will explain what I mean by this when we get there. But some of the topics that we'll discuss will include how to scale up data collection, how to allow, how to have robots to collect a lot more data than they're collecting currently, and how we can utilize broad offline data sources, including non-robotic data sources, and then how we can apply reinforcement learning to lifelong settings as well. And then at the end, we'll also discuss open challenges. All right, so let's start with utilizing zero-shot generalization of large language models. So just a few words of introduction. Well, what is special about large language models? There's a lot of hype around them, and maybe the hype is a little bit too much. But the one thing that is extremely exciting about them is their ability to perform zero-shot generalization. And Colin in his lecture talked a little bit about how they could be viewed as models that do implicitly meta learning, but their zero-shot generalization is something that we really haven't seen at that scale, and that makes them extremely exciting and extremely useful for other domains as well. So with that, I would like to welcome Eric Mitchell, who will tell us a little bit about how we can fine-tune these large models, what are the difficulties that come with that, and how we can do this better without having any negative transfer. So Eric Mitchell is a PhD student with Chris Manning and Chelsea Finn. So Eric, please take it away.
Yeah, thanks for the lovely intro, Karol. Great to be here and talk for just a couple minutes about our work. Maybe if you could stop sharing your screen, I can show. I've got some slides. Perfect. Thank you. So yeah, as Karol mentioned, I'm going to say a couple words about fine-tuning on basically one example without negative transfer, which we can sort of think about as editing a pre-trained neural network. So I'll get right into it. Basically, what do I mean by editing a neural network, and why do we want to do this? Well, I mean, you're probably familiar with the fact that when we train a neural network on some big data set like ImageNet or Wikitext, they end up sort of soaking up a lot of the knowledge one way or another in these data sets. But obviously, as Sam Altman pointed out in his tweet, even a big model like GPT-3 is still wrong. And even when they're correct at the moment that training completes, over time, their predictions may become obsolete. So as an example, if we take some more or less state-of-the-art question answering model, like T5, and we ask it who the Prime Minister of the UK is, it's going to say Theresa May. And depending on how familiar you are with UK politics, you'll know that this is not the Prime Minister of the UK, though it used to be. And so this just reflects the fact that this model was trained on data that was gathered in the past. And so ideally, what we'd like to be able to do is locally tweak our model's behavior on sort of this one example without destroying its representations and its predictions on other parts of the input domain. And this problem isn't really specific to language models, although they provide sort of a convenient modality to highlight how this failure occurs. We can come up with examples with image classifiers kind of screwing up when they're exposed to one particular background, but not otherwise. Policies that make mistakes in one particular configuration of the environment, not others. Translation systems, mistranslating particular phrases between particular languages, and so on and so forth. So it's a fairly general problem that crops up when we sort of start to deploy these models and then time goes by. So in other words, the model's mostly right, but we want to figure out how to change it for kind of just this example and the related examples. So how do we actually do this? Well, if you squint at it, it's sort of like one-shot learning in a way. I mean, we get one example and we get the label for that example, and we want to correctly change our model for that one example. So in our sort of normal few-shot learning setup, we're going to have some metadata set, where here our metadata set is a data set of individual questions. And each question is sort of a different one-shot learning task. So we have kind of X-edit, the input, the question, Y-edit, the true label for that question. And then X prime is sort of our like query input, like a rephrasing of the question to see if our one-shot adaptation actually generalizes. And so as an example of this, we would have X-edit as like, who's the PM of the UK? We would put this through our pre-trained model, and we would say, well, it says Theresa May instead of Boris Johnson. That's not so good. And so that's sort of our support example. We would give it a support label, essentially, which is the edit target, Boris Johnson. And then we have a query input, X prime, which checks if the model correctly, has changed its predictions, not just for that exact input, but for related ones. And so this is basically one-shot learning. But this doesn't really fully get at the editing problem, because we have an additional issue here, which is after we've performed this edit, we want to make sure that our model is making the same predictions on unrelated data as it did before we made the edit. So if we have this sort of control input X lock, this sort of locality constraint, like who is the president of France, if we change the prime minister of the UK, we don't want to change the president of France. And so we want to have an additional constraint that's not only saying after adaptation, what is my model doing, but it should also be constraining the difference in the behavior of the model before and after adaptation. So this is a little different than normal few-shot learning. And so at this point, you might think, well, okay, we have this sort of slightly different loss function. Let's throw MAML at it or some other algorithm. But there's sort of one other consideration, which is that as opposed to maybe normal meta learning, where we start out with sort of a random model and then we meta train it so that it's good at adapting, in this setting, we're actually given a pre-trained model up front. And so we don't actually want to change that model initialization, because the pre-trained model, we are assuming, sort of performs well most of the time. So somehow we need to do the meta learning without changing our initialization. And this makes it difficult to straightforwardly apply an algorithm like MAML, where the representation power of meta learning comes from this really big parameter space in the model initialization. So instead, what we're going to do is we need the meta learner to be separate from theta. And so one way or another, we need to parameterize some transform of the update, which are these, one way or another, these little networks that basically take the fine-tuning gradient and map it to a new sort of pseudo gradient, which provides the properties that we want for edits. And so this is sort of the framework that we've been thinking about for editing. And you can do some pretty interesting things that basically give the behavior that's shown in this diagram here. So to recap, editing models lets us locally adjust their behavior after training, which can be useful in sort of a wide variety of circumstances. And it's sort of like one-shot learning, except we have these couple of different tweaks to the setup, including the adaptation should only be a local change, and then we also sort of don't really want to change the initialization during the course of this meta training. So hopefully that was presented in a way that was somewhat parsable. If you're interested, there's a paper that we've recently put on archive called Fast Model Editing at Scale.
Thank you so much, Eric. Are there any questions? We have a little bit of time. So if there are any questions from the audience, please just speak up or raise your hand. Actually, I have one question. Do you think that changing or modifying the gradient itself, the way you are doing it in this paper, could be applied beyond, editing large language models, but could be also a different form of meta learning in general?
Yeah, for sure. I mean, there are sort of a handful of different algorithms like meta curvature or warp grad or meta SGD, et cetera, that are basically learning some transformation of the gradient. Maybe they also learn the initialization, but they sort of add this expressiveness by transforming the gradient. And yeah, I mean, this seems like it could be pretty directly applied to these settings. And we kind of came to it motivated by the editing problem, but realized sort of the solution is actually probably quite a bit more general than just this specific setting. So yeah.
Awesome. Cool. Let's see, are there any questions from the audience?
You have one?
Yeah, I see raised hand.
Yeah, this is pretty fascinating. I was wondering a little bit about the down the road kind of applications. If you could speculate a little bit about that, is it more of like you have a language model that you train and it's mostly right, but there's some cases you want to get that it gets wrong that you want to fix, or maybe could it be like with the UK Prime Minister example, that's something that's changing constantly, and so like more of like oh, this needs to be updated because of changing times.
Yeah. Oops, sorry.
Yeah, just any thoughts about that?
Yeah, sure. So I think the immediate application is more like what I presented in terms of, we maybe Google deploys a translation model and they get like a handful of user reports every day. And ideally, you'd have some sort of pretty quick automated process to be able to take these user reports and sort of inject them into the model quickly so you don't have to retrain or go through some long process to fix the model. And these might be due to just errors during training or temporal shift. I think longer term, it would be interesting to sort of start tying this editing, direction into more like continual learning settings where we don't want to just sort of do one edit or a big batch of edits once right up front, but ideally we have some way to sort of either take a pre-trained model or tweak a pre-trained model such that we can sort of successively patch it in this way and not sort of compound this drawdown that's incurred every time we do an edit. So I would say longer down the road, you sort of want to tie it with continual learning.
Thank you.
Sure.
Right, great. Thank you, Eric, so much. Feel free to drop out of the call. I know that you're busy. Thanks so much. All right, so we talked a little bit about how we can fine-tune or edit these large language models. Let's see, does this work? Let's talk a little bit about how we can apply these large language models to other domains. So there is a little bit of work on applying large language models to other domains that still involve language. And there's some interesting work coming from OpenAI that talks about solving math word problems, for instance, where given a math question like this, Ali is the dean of a private school where he teaches one class. John is also the dean of a public school. John has 2 classes in his school. Each class is 1/8 the capacity of Ali's class, which has the capacity of 120 students. What is the combined capacity of both schools? It turns out that they can train a model that is pre-trained on GPT-3 that can actually answer that question correctly. So they take that question, put it in a prompt for a large language model, and then the model is able to output the correct answer. But it turns out that actually just fine-tuning that model to these kind of questions doesn't work very well. So instead, what they do is they train an additional model that does verification. So given a set of different answers and the question that was originally asked, it can just discriminatively say which answer is correct, or if there's no correct answer, to say that there's no correct answer. And it turns out that this model actually provides quite a bit of boost of performance. And it's much easier to train a model to verify the solution than to fine-tune a model to always propose the correct solution. So then at test time, they would have the large language model produce a set of different solutions and then use the verification model to verify which one is correct, and that achieves fairly high result. At OpenAI, they've also showed some applications of large language models to something like code completion, where you can, where they introduce this tool called Codex, where you can specify the instruction that you would want the model to help you with, to specify the code for. Then that instruction is then changed to to look like a comment. So they take the prompt, they put it as the comment for a Python code that will be generated. That model was then fine-tuned on a lot of Python instructions associated with the comments as well. And then the large language model outputs the Python code that is being executed, and you see the results of that. And there's obviously many applications of that as well, starting from just helping us be better coders, but also like a really interactive tool that would allow maybe more people getting to coding. So these are some applications of large language models that we see today that still involve a lot of language itself. But I thought that one interesting topic would be to talk about how large language models can be applied to other domains that maybe are not necessarily connected to language, such as robotics. So with that, next we'll talk about how to apply large language models to other domains. And I would like to invite Eric Zhang, who is a senior research scientist working at Google Brain, at Brain Robotics, where we work together on a lot of these problems. And Eric will talk to us a little bit about his work on that topic.
Thanks for the intro, Karol, and for inviting me to give a quick talk on this this project that we did at Google. So yeah, my name is Eric Zhang. I'm a researcher at Google working on robots. So I'll be talking about BCZ, zero-shot task generalization with robotic imitation learning. Here's a list of the collaborators, the usual suspects in large-scale robotic learning. So as a quick preliminary, can we learn tasks in the real world with deep learning on robots? And the last few years and many years before that have suggested that the answer is yes. So you can do single task learning with pick and place, and it generalizes to a variety of objects. You can do cable insertion, and it also generalizes to different situations. Block stacking also generalizes. In this work, we also study a little bit of pick and place as well. But as I'm sure many of the students in this class are interested in, can we kind of get one network or one policy to learn multiple tasks in the real world? And again, the answer is also yes. So some of the work by Karol and collaborators have done this on MTOpt. There's some other work with transporter nets and task embedded control networks, all suggesting that, unsurprisingly, you can get robots to do multiple things, and there's some sort of generalization and knowledge transfer between there as well. So the goal of this work was to look at whether robots can learn tasks that they haven't been trained on in the real world. So not only are we doing multitask, but we want to generalize at test time to new tasks that it hasn't seen demos for. The setup is very simple. So we collect a lot of data with expert teleoperation on 100+ manipulation tasks. We use pretty much the simplest learning algorithm possible for learning visual motor control, which is imitation learning. So image in, action out. We regress this to expert demonstrations. And then at test time, we command it with a new task, and it'll just generalize to new instructions. So in the blue squares here, you see some of the training task sentences, like place the bottle in ceramic bowl, place the bottle in, knock the eraser over, and so forth. And then the green boxes contain test tasks for which the instructions we've never trained the policy on. The model architecture is very simple. It's just a modification of a ResNet, and the ResNet takes in a frozen pre-trained sentence encoder embedding or a video encoder embedding. I'm just going to talk about the sentence encoder aspect of this in this talk, but you can think of them as interchangeable. So we have the training tasks divided into two sets of objects. The object set on the top contains tasks like place the sponge in the ceramic bowl, and the object set on the bottom, which has mostly different objects, has things like wipe the tray with sponge, or put this cup in that other cup, and so forth. So the cool thing about training all of these tasks is that we kind of get generalization through the magic of deep learning, which is that at test time, you can mix together objects in these different object sets and command it with a natural language instruction that it's never been trained on before. So it's never seen like the grapes and the ceramic bowl in the same image in the training data. And it hasn't been trained on the sentence, place the grapes in the ceramic bowl, but it'll still generalize and do the correct behavior. Here's some other videos of the held out tasks that it can do. And so what are the takeaways here? Well, so we've seen that the system, which we call BCZ, generalizes to unseen points in some pre-trained frozen task embedding space. And if you'll permit me some, wild speculation here, I think that large language models are much more than a way to provide a policy with a task. So, I mean, that's what we do in this paper, but as you can see from our results, language allows you to compose semantics together, like unseen subject, object, verb combinations. But beyond that, language has a lot more kind of power than that. So there's this idea of like Chomskyan recursion, which is that you can embed clauses inside of other clauses, and you can do this over and over again. You can perform logical reasoning within language, as you've seen with these OpenAI codex examples. And sometimes even like fuzzy logic is okay. So when you write like a programming doc string, it's kind of like logical, but not really. And still like language models can understand that. So if you believe that large language models can do this, then it might be a really nice substrate for improving generalization. And in machine learning, we have this perspective that generalization is like this notion of invariance. So you see different images, but ultimately, like the things that you see at test time, even though you haven't seen them before, they kind of mean the same thing as something you saw at training time, and that's what allows robots to generalize to new scenes. The linguist view on generalization is that words are some sort of discrete unit of meaning, and language is about composing discrete tokens into more complex meanings. So as a recipe for kind of making more powerful, more general systems, maybe what we should do is take our data, like robot episodes or something, we pair that with a bunch of rich human language, for example, by just describing it. And then we train some sort of data model jointly with a language model. And we use the language aspects of compositionality and recursion and logical reasoning to then now compose and control the data in any way that the language permits, which is pretty much everything. So I have a blog post where I talk about this called Just Ask for Generalization. If you want to take a look. And I think that's my time. So thank you very much.
Thank you, Eric. Are there any questions?
I have a quick question. Super interesting work. I'm curious, like, if you see any sort of limits in the pre-training procedures we use for these large language models, and basically, like, if you could pre-train that model yourself, or if you could make a little adjustment to how that model was pre-trained, do you think there's a lot of sort of headroom still to squeeze a lot more kind of compositionality or recursion from those models, or do you think the pre-training we do now is basically like the vast majority of the benefit we're going to get from these?
I don't have a good answer for that. If I had to take a guess, probably like some fine tuning would be necessary, because like aligning the language compositionality and generalization to like what you actually want at deployment time seems tricky, and maybe additional kind of feedback via fine tuning and customized data collection would help.
Awesome. Do we have any other questions from participants? I would actually have one question to you, Eric, as well. Do you think that it's really interesting, the perspective that you said at the end, that maybe we could just collect robotic data and label it with language and then just ask for what we want? Do you think there's an equivalent to, there always exists a language prompt that you can specify that would be equivalent to an existing algorithm that we already have? Basically, does this mapping always exist, do you think?
Are you saying, like, is it possible to get the behavior of any algorithm by conditioning on language?
That's right.
So
yeah.
I would argue yes, because language also supports, not only does it support fuzzy logic as we see in the codex, but it also supports like concrete logic. You could just put in the tokens of an actual program into the language string, right? So if your neural network learns to do program interpretation, then it could conceptually do that as well.
Cool. Very interesting. Right, I think we have one raised hand.
Hi, thanks for the great talk. My question relates to long horizon tasks and, like, let's say longer commands language sequences, and how the actual performance varies for longer horizon tasks. And if you have any ideas on overcoming some of the issues that are faced with, like, learning a policy for a long horizon task in this setting.
Sure. So I'm just going to kind of focus on the kind of concrete robotic results and not any of this kind of speculative language stuff. So in general, learning longer horizon tasks is much harder than learning short horizon tasks. And we see that there's a strong negative correlation between the length of a demo and our learned policies success rate. So we're controlling at 10 hertz, which is pretty high frequency for robotic deep learning. And as a result, our performance numbers aren't super good. But yeah, like they're in the like 100 to 200 number of decisions. I think this is more of like a, how do you get reliable learning in these kind of hard MDPs? Yeah, so it's an open problem in the field.
Thank you.
All right, thank you. Thanks, Eric. Next, we'll have Corey Lynch, who is also a senior research scientist at Google Brain, where we work together on some of these things. And he will talk to us a little bit about language conditioning imitation learning as well, but it will be slightly different. And I think there may be some different conclusions also about using large language models. So Corey, please take it away.
Great. Thank you, Karol. Hi, I'm Corey, and like Karol said, I'll be presenting some joint work with colleagues at Google Brain on combining robot learning with large language models. Yeah, so much like the last talk, the setting that we're interested in is a single robot that can learn a very large number of tasks. And furthermore, we'd like users to be able to specify any of these tasks in free-form natural language. And also like the last work, we're restricting our attention to just simple supervised imitation learning. So a typical multitask imitation learning setup might look like this, where you collect a large number of demonstration data sets for each task, you perform supervised learning, and then at test time, you might condition on things like one-hot task IDs. But if you'd like to scale to a very large number of text commands, for imagine like push the button, or even something like move your hand back slightly, something more interactive, you can imagine that these collection requirements might actually get quite expensive. And this mode of behavior conditioning could become pretty inflexible. So the main questions we asked ourselves in this work were, how can we lower the collection requirements? Can we instead learn a large number of skills self-supervised from unlabeled data that's much less expensive to collect? And second, if you've learned a lot of these behaviors, how can you actually condition them with things like freeform text? And then finally, this one's kind of subtle and specific to text conditioning. Language can almost be too flexible. There's so many ways that you can think of describing the same task, it's unlikely that you actually cover them all in training. So how can you solve for new synonym instructions at test time without having to collect new robot data? So I'll quickly describe our approach. The first ingredient is a large unstructured play data set. Here, a human teleoperates the robot and plays with the objects in the scene in as many ways that they can think of. So you can see there's no upfront task definition and no resets. And this is important because it means humans can quickly collect lots of demonstration data covering many tasks. And so we see a lot of behaviors on display here. How do you actually train a robot to execute specific ones from text descriptions? So say you've collected a number of hours of play, you can now consider all 1 to 2 second random windows. And one thing to note here is that each window contains the exact information for how the robot got from an arbitrary start state to an arbitrary end state. And nothing stops you from treating each of these as demonstrations for how to reach goal images with a robot. At the same time, we can send less than 1% of these to crowdsourced annotators. And after watching a video, we can ask them, what text instruction would you have given the robot to get it to go from start frame to end frame? And so in this way, we can efficiently mine 2 demonstration data sets from play, one big one solving for image goals, and a smaller one solving for text goals. So say you have these data sets, rather than train a separate policy on each, we're now instead going to train one big policy to solve for either image or language goals. And you can also think of this as just doing language conditioned learning with an auxiliary self-supervised loss to improve sample efficiency. And we found that this sort of shared training scheme is actually fairly important. It allows us to reduce the cost of language annotation to less than 1% of the collected robot experience. And so at test time, we're only going to use text conditioning. Here's an example of a human typing free-form natural language commands to the agent. You can see the robot executing multiple of these in a row. And the agent's receiving onboard RGB camera input and free-form text instructions, and then producing actions in closed loop at 30 hertz. So in the interest of time, I'll refer you to more videos at the link above. But then, so yeah, we've now described a system that can, 1, learn behaviors from unstructured data, and 2, kind of allow people to command these with natural language. What about number 3? So in our experiments, we found a simple and what we think is actually like a fairly generic solution to this. Instead of learning on top of raw text instructions, first embed them in the space of a large language model that's been pre-trained on web scale text data. So why do this? Pre-trained language models have been shown to become synonym aware, meaning they can map at the sentence level two disjoint but semantically similar sentences to the same region of embedding space. And so by doing robot learning on top of pre-trained embeddings, the language model is responsible for mapping new instructions at test time to ones that the robot has already been trained to follow. And so we think this is a pretty nice separation of concerns. This means that the policy itself doesn't need to know how to generalize. It's just the language model that needs to know how to generalize. And so practically, this means that your agent can now follow thousands of new synonym instructions at test time in zero shot without requiring new robot demonstrations, which is good because robot demonstrations are expensive. And another nice thing is that if your pre-training process happens to be multilingual, this means that you can even follow instructions in new languages that you've never collected. So this is what you see here. This is our agent following zero-shot French, even though it's only been trained in English. And I think this really illustrates the power of this. Like both me and the agent have only ever been trained to follow instructions in English, but by just applying this trick, my agent suddenly knows how to demonstrate physical knowledge in French. So I think this sort of trick highlights like we're really only scratching the surface of the knowledge that can be transferred from large language models to robot learning. And so I think there's a lot of exciting ways that we can think of transferring even more of this knowledge. Thanks for your time. If you'd like to learn more about this work, feel free to check out our paper or more videos on the project page at language-play.github.io. Thanks.
Thank you, Corey. Are there any questions? I'll have one question. Have you noticed, or I guess it's a little difficult to evaluate this, but can you tell whether you can also generate new motions that you haven't seen before by conditioning on language in different ways? So it's not just necessarily indexing what it's already seen, but maybe it can also generalize to something that it's never seen before.
Yeah, I think given the fact that I think this might be easier to kind of study in a controlled setting where you didn't have like the unstructured demonstration data, because it's fairly hard to guarantee that you haven't seen this motion before. But I think it's a very interesting question, and it's probably worth some study. Like, can you actually, by conditioning on kind of a new region of language space, get some sort of like interpolative, nice action behavior that you can prove has never been seen in training? Maybe hard to study in the exact setting that we described here, but I definitely think it's worth studying in like a new setting.
Awesome, thank you. Any other questions from the participants? We have a raised hand.
Yeah, hi. Yeah, I guess my question is for both, I guess, your work and Eric's work as well. Is there a reason most language work nowadays kind of focusing on imitation learning and not reinforcement learning directly, so that you can kind of get broader than just the play data and maybe start learning newer things that's not in the play data as well? And I guess,
Oh, sorry.
and also I guess I don't know if you have any distribution shift issues. If you just do imitation learning and yeah, the usual issues with behavior cloning, I guess. Do you think we can do reinforcement learning with language?
Yeah, I mean, I think there's a lot of really interesting reinforcement learning language plus language work, and I think you might even be hearing about some really interesting applications of that, right? Kind of in the following speakers. But at least for us, the reason that we restricted our attention to imitation learning was to avoid kind of questions like how do you specify rewards in the real world? How do you do like meaningful exploration, targeted exploration? Kind of these are like thorny questions when you try to scale up to robotics. And so at least for us, the question was like, how far can we push simple imitation learning kind of until it breaks? And as for things like distribution shift, if you check out the paper, we actually have some like interesting results about the robustness of policies when they're trained over unstructured data, as opposed to kind of more rigid curated data sets. precisely to address these things like distribution shift. So just by training on kind of like more diverse data, you can show that these policies at test time are a little bit more robust to perturbation and kind of distribution shift than if you had trained them on kind of more rigid and kind of curated data sets. But that being said, it is still imitation learning. So the problem is you can of course get off of you're still subject to all of the compounding error. You don't have like a generic solution.
Got it. I guess sorry, just one more follow up. I guess if you're labeling play data and then imitating on it, I guess also there might be an issue of if the play data to, like, let's say, move up from the top shelf to the bottom shelf isn't exactly optimal because maybe the human is doing it in a suboptimal way, and then if you label it with that language instruction and imitate, then I guess you may be learning a suboptimal trajectory for that language instruction. Unless I guess if the play data is large enough, this won't be an issue. But
yeah, so if the key thing here is that we're restricting to short horizon behaviors, and so certainly for like a long enough horizon, you might do a lot of suboptimal things in between getting from the start state to the end state. But at least by looking at like 1 to 2 second windows, empirically, just by like watching a lot of these videos, you can kind of convince yourself that a lot of these are like fairly optimal for the short horizon of like straight line reaching start state to end state. And you also get kind of text instructions paired to windows that are like move your arm to the left and then move it back. So not necessarily tasks you would ever command, but more just descriptions of what's happening.
got it. Thank you.
Right. Thank you, Corey. And since there was a question about using language in reinforcement learning, our next speaker will talk exactly about this. So next we have Suraj Nair, who is a PhD student with Chelsea Finn, who will tell us a little bit about how we can apply large language models or language in general in reinforcement learning. Take it away.
Great. Thanks, Karol. So hopefully everyone can see my screen. I'm Suraj. I'm a PhD student with Chelsea, and this is some work we did in our lab and with some collaborators at Google as well, called Learning Language Condition Robot Behavior from Offline Data and Crowdsourced Annotation. And the broader goal in this work is kind of similar to the few prior presentations as well, as we want to learn, have our robots be able to learn from large offline data sets to be able to many different downstream tasks. And particularly, we'd like to be able to learn from kind of non-expert offline data. And in this paradigm, humans need sort of easy and effective ways of actually specifying these tasks and the rewards and success criteria. And so, one common approach that's used is goal images, right? So you could have an image that specifies the task, and many prior works have done this, and it's a natural choice because these goal images exist in the data set already. But there's a number of drawbacks, like a human actually needs to go in at test time and create this goal image to specify the task, and it can often over-specify the task, like different objects that are not task relevant, can't specify persistent behavior. So in this work, the question we're looking at is, well, can we actually do this with natural language? Like, just say in this case, push the ping stapler forward. It's much easier for humans to provide and can flexibly represent many tasks. So a little more concretely, kind of in this work, we're trying to learn language conditioned vision motor manipulation skills on robots from offline robot data and crowdsourced annotation. And critically, we want to learn from potentially highly suboptimal offline data that's not expert data. And so this might be, for example, data from some agents that it's exploring autonomously, or maybe reusing the replay buffer of a previously trained RL agent. And then we want to have crowdsourced annotation tell us, what tasks, if any, are happening in this data set. And the kind of key idea in our work is that, we can't necessarily treat the actions in this data as optimal. But what we do know is even if the agent took some suboptimal trajectory, going from the beginning to the end of an episode is going to complete, whatever instruction the human annotated it with. And we can then use this to learn a language condition reward function that can be used for offline reinforcement learning. So at a high level, our approach is going to look like we'll have some offline data. We're going to get a crowdsource, have annotators kind of annotate what is happening in each episode. So some episodes it might be do nothing, some episodes it might be try to insert the marker into the hole. And we're going to use this to learn a language conditioned reward function. In the interest of time, I won't go over the details on the exact offline RL method we use. Like in our case, we use a model-based approach, but kind of the key component here is really in learning the reward function that you can use kind of with whatever your favorite offline RL algorithm is. And how do we actually learn it? Well, the reward function we train is basically just a binary classifier of instruction completion. So it's going to take an initial state, a final state, and some instruction, and it's going to predict, does transitioning from that initial state to final state complete that instruction? Collecting positive examples for this is straightforward because we have episodes in our offline data and their corresponding annotations that we can treat as positives. And you can actually generate, basically as many negatives as you want by randomly kind of combining episodes with different instructions and take an instruction from a different episode and put that in place, or reversing the episode to basically get these negatives. And this classifier is going to use a pre-trained language model, and we'll see a bit more about this in a few slides in the experiments. But basically, using this pre-trained language model enables some generalization even when you have limited grounded data of episodes and their corresponding annotations. So I'll skip over the kind of control part for now, and move on to just some of the highlighting the experiments. In the first one, we were basically just looking at how does this compare to using like goal images as specification or imitation learning. And the key takeaways here are that, because the data we're trying to learn from is really suboptimal, if you were trying to imitate it or do language condition imitation on this data, it's going to perform poorly. Whereas using our method, you can actually improve over the behavior policy that collected the data. And it also outperforms, say, using goal images as your task specification, because those are kind of prone to over-specifying the task. The next thing we look at is generalization to unseen kind of phrasings of your different commands. So, for example, we might normally be evaluating on tasks like close the drawer, turn the faucet left, and we look at, okay, what if we swap out the verb or noun or both with an unseen one, or we actually sent out a survey to the lab and said, phrase this instruction in some creative way. So instead of saying like turn the faucet left, someone you might say spin the nozzle left. And what we see is that with our method, we're actually pretty robust to these rephrasings with like at most a 10% drop in performance. And using a pre-trained language model is critical for this. If we don't use a pre-trained language model, performance across the board is worse, even on the seen instructions, and performance degrades a lot more when you're giving unseen instructions. So the pre-trained model is pretty important for this. And then the last thing we looked at was trying to actually use this on a real robot. So we took basically the replay buffer from a totally different project, which was just 3,000 episodes of the replay buffer, trying to do various skills on this desk of this robot interacting on this desk, consisting of many kind of successful and unsuccessful attempts. And then we would crowdsource annotations for this, and then use our method. So this is sort of the interface we gave to the annotators, where we say, okay, describe what the robot's doing as a command, and then if you're not sure, right, do nothing, or you can't tell, right, NA. And so we got a lot of kind of very creative annotations from the crowdsourced workers, things like rub the drawer handle, hit the rack with the marker, but despite how noisy they were, we're still able to learn to then be able to specify the robot to do tasks like open the left drawer, open the right drawer, moving the stapler, and reaching like the markers or reaching the cabinet, and also being robust again to sort of different ways of rephrasing the task. So instead of saying move the stapler, we could say push the small gray stapler around on top of the desk. And again, I would say largely due to the pre-trained language model, it's still able to complete these tasks. So just to sum up, I think the key takeaways are, to have multi-effective or useful multitask robot policies, humans need easy ways of specifying tasks like natural language. And then using our method, we can learn these language condition policies from very suboptimal offline data. And then lastly, the pre-trained language models are important to actually being able to generalize to unseen tasks. And while we don't actually have an experiment testing this, I suspect that it's critical to being able to handle the diversity and crowdsourced annotations when you have annotators giving you all sorts of funny ways of phrasing what the robot is doing. I think without the pre-trained language model, it would probably be very difficult to learn from that. So yeah, that's it. Thanks.
Thank you, Suraj. Are there any questions? In the interest of time, I won't be asking a question myself. Let's see if there's anybody. Right, I don't see any questions now. If you have any questions, please just write them in the chat. And I think maybe Suraj, if you can stick around for another 5 minutes or so, that would be great.
Sure.
Thank you, Suraj. So yeah, we talked about how we can fine-tune these large models and then how we can apply large language models to other domains, such as robotics with reinforcement learning or imitation learning. A few takeaways. We can transform the gradient updates that can allow us to edit models efficiently. And then we can also use large language models to boost generalization. And we've seen a few examples in robotics that show how we can generalize to new text commands, how we can potentially generalize to new languages even, potentially doing new tasks, and maybe even more. As Eric was saying, there's a potential that, there's a lot of potential with these large language models, how they can be used. So next we'll talk about how we can make reinforcement learning a better data sponge. So what I mean by this is that if we look at large language models, for instance, or any supervised learning recipes right now, they require a lot of data and very expressive capable models that can digest all of that data. So in other words, they're able to absorb large amounts of data. They're really good data sponge. And large language models is a perfect example of that, where they can just go over the entire Wikipedia and take all of the data in. And as a result, we get really good generalization out of these models. So we can prompt a model that was trained like that with something that is pretty clear that it shouldn't have seen before, such as create an image of a snail made out of corkscrew. And it actually does a pretty good job doing that. Now, if we compare it to reinforcement learning, in reinforcement learning, when we usually talk about data we digest, it's usually something like this. We just have a half cheetah, and that's the only environment we train on, and we evaluate on the same environment. Even if we expand on that and use something like meta world that we discussed before, if we look at performance of these multitask reinforcement learning algorithms, they don't seem to work very well across many different tasks with different reward functions, different difficulties of tasks, and so on. So if we were to draw a data sponge analogy for this, our data sponge is not very absorbent for reinforcement learning. So I think one kind of set of really interesting directions and interesting works is how we can make this data sponge for reinforcement learning much more absorbent. So rather than working maybe on better sample complexity, so how to use less data, how we could work on algorithms that can utilize and digest more data, be a better data sponge. And in that vein, we'll have 4 presentations. And first, we'll start with how we can, in the first place, just scale up data collection itself. And to talk about this, we have with us Archit Sharma, who's a PhD student with Chelsea Finn as well. Archit, please take it away.
Great. Hi, everyone. I'm your favorite TA, Archit, and I'm going to be talking about what I do outside holding office hours and making assignments. More specifically, I'm going to talk about RL. And as I think Karol already said, we need to get more data. And I'm going to talk about why RL is not able to scale up data collection at this point. And I would suggest this boils down to making RL more autonomous. The motivation begins with comparing with how humans learn. And in this specific case, we are looking at example of how a human juggles balls and how they're learning. And this is obviously a very difficult task. So the human needs to practice this task several times. But the important point that I would like to emphasize here is that that the human doesn't need external help while practicing this task. So the balls fall down, they pick it up, they start again, and they improve by themselves. And this is a very important point because to me, this is the gold standard of autonomous learning. Now let's contrast this with how like robots actually learn. And again, in these specific examples, the first robot is trying to hit the puck into a goal. And in the second example, the robot is trying to open the door. So in this case, whenever the robot needs to practice again, a human first needs to intervene into the data collection, and then it needs to reset the environment so that the robot can start practicing again. I hope at this point, it's very clear that the way robot learning proceeds is far from autonomous. Even though RL is such a great paradigm for learning, it still relies on humans fairly heavily. Now, learning autonomously isn't just about mimicking humans. This leads to practical problems as well as some of the previous videos suggested. So more specifically, let's look at how RL works. It starts off with the state S0, and then RL relies on collecting trajectories in the environment and it collects a sequence of takes a sequence of actions and collects a trajectory like this from S0, A0, S1, S1, and reaches a state SH. After a point, we terminate this trajectory, we reinitialize the environment at S0 prime, and it collects a new trajectory in the environment. Now, reinforcement learning obviously relies on a lot of practicing in the environment and collecting a lot of trajectories like this. But the big question is, who takes the environment from the state SH to S0 prime? And this might not seem immediately obvious, but based on the examples that you've seen thus far, this often ends up being humans. And this ends up being a major problem because you're almost always reliant on humans being there for the robots to continue learning. Now, assuming like you buy this premise, we decided, wait, we should first look at like, I mean, it's very easy to ask the question that what if we just run our algorithms for longer without resetting the environment? And this is kind of the question we investigated as well. What if we just take our basic algorithms and just run them longer? So we started with giving resets every 1,000 steps, and we increased this to 200,000 steps. And as you can see, the performance depreciates quite a lot, which kind of suggests that the algorithms that we have right now are not exactly capable of operating autonomously, and they're very heavily reliant on humans. So motivated by this, we decided that we should maybe change the problem itself. We should realize the constraint that humans are not there to intervene for the robots to continue learning. And so I'll skip a few details here, but the broad goal here is that the robot should continue interacting and learning with the environment. And it's initialized at that environment once in the beginning, but after that, the interaction continues for posterity. In formal terms, this will continue for an infinite horizon, but there wouldn't be any resets to like generate new trajectories in the environment. And there are a few metrics that we can optimize for. But broadly, we want to learn good behaviors that robots would want to like execute or be used for. And this is what we want to learn autonomously. Now, this is a really hard problem. And the way we do reinforcement learning clearly is not sufficient for it. So this motivated us to create a nice benchmark where we have a diverse collection of tasks, which are representative of realistic scenarios. And we wanted to like encourage the community to come up with algorithms that can actually learn without humans, because that would enable us to run robots for longer, collect a lot more data. And I would point out like a surprising result towards the end as well. And some of the tasks we consider are manipulation related tasks. We have a multitask kitchen environment as well, where you have a diverse set of tasks as well. We have locomotion, and we have some like high dimensional dexterous hand manipulation tasks as well. And we strongly want the community to participate in like improving the algorithms and developing better ways to scale up data collection and do RL in general. Unfortunately, I do not have the time to go into the details of how to build these algorithms. So I'm going to drop some references here, and always feel free to reach out to me. But one thing I do want to like point out to like keep the excitement is that when agents learn autonomously, it naturally leads to a robustness. As you saw in the example of how human is learning, they learn to correct their own mistakes. And this is a big part of reinforcement learning. But learning autonomously encourages robustness in even more. And this is really desirable for practical robot learning or practical embodied agents. And to quickly explain the bar graph here, the oracle is the policy that learns with resets. And we see a much larger drop in performance from the gray bar to the green bar when the conditions it trained on changes. Whereas the FBRL and VAPRL are two different autonomous algorithms and basically have no drop in performance when especially VAPRL doesn't have a drop in performance when the initial conditions of the environment changes, which suggests that if you learn autonomously, you would end up learning robustly as well. So yeah, that's my talk, and feel free to reach out to me on Ed or whatever. So yeah, thanks.
Thank you, Archit. Thank you so much. In the interest of time, I will ask people to ask questions in the chat. For now, actually, we have one quick question. Let's do it.
Sorry, so quick question. Is it still considered autonomous learning if you have a secondary robot reset the environment for you? I noticed that in like one of your examples, video examples, a door was opening and closing and the human had to close the door. Couldn't that have easily been solved by having a servo?
That's exactly one of the tasks we have in the benchmark and how you should do it, because the same robot can actually learn how to open and close the door, right? It doesn't need to be done by the human. So if the robot, like, there are ways to script these things as well. So, but the idea is that we don't want to like spend a lot of time with us doing the effort, but we want robots to learn without us expending the effort. So this is exactly one of the tasks we have in the benchmark as well.
I see. Thank you.
Yeah.
Thank you. Thanks, Archit. And yeah, if you have more questions, please ask them in the chat. All right. So we talked a little bit about how we can scale up data collection. Let's now talk a little bit about how we can use broader data sources, how we can actually make reinforcement learning a better data sponge. So next up, we have Annie Chan with us, who is a PhD student with Chelsea Finn, who will tell us a little bit about how we can use other data sources as well. Annie, take it away.
Great, yeah. So as Karol mentioned, hi everyone, my name is Annie Chen, and I'm a PhD student working with Chelsea. And I'll be sharing a little bit from a recent work on learning generalizable robotic reward functions from in the wild human videos. And yeah, this is a joint work with Srajner and Chelsea. So we're motivated by the overarching goal of a general purpose robot that's capable of completing a wide range of tasks across many different environments. So towards this goal, an agent must be able to acquire some metric of task success or reward signal. And this is necessary for like reinforcement learning, planning, knowing when to ask for help. So here we're focused on learning reward functions, which allow a robot to determine its own proficiency at a specified task. We're particularly interested in how reward functions that can generalize across varying environments and tasks, because otherwise we can't hope for our agents to be able to use them to learn general purpose policies. So a promising path towards this goal is to leverage large and diverse data sets, which we've seen have been important in achieving broader generalization capabilities in computer vision and NLP. However, collecting large amounts of diverse interaction data on real robots can be pretty challenging and time-consuming. So alternatively, in the wild, videos of humans is this huge source of very diverse data that already exists. And so if we can teach robots using this sort of data, we can greatly increase the diversity of the data that our agents can learn from without much additional overhead. However, learning from this sort of data is very challenging for a number of reasons. So first, there exists a large visual domain shift in the observation space. Second, there's no clear mapping between a human's action space and a robot's. And lastly, in the wild, human videos may often be low quality and noisy. So how do we leverage this data for a reward function? The key idea to our approach, which we call domain agnostic video discriminator, or DVD, is to train a discriminator that looks at two videos and outputs whether they're completing the same task or not. So we train the discriminator to predict 1 if two videos are doing the same task, and 0 if they are completing different tasks. We can then use this discriminator in conjunction with any human video demonstration as a reward function to solve the task that's specified by that video. So unfortunately, I think I'm going to have to skip the specifics of that for time. But what this actually looks like is, given a human video demonstration for closing a drawer, our method enables the agent to close the drawer in these unseen test environments. And here's another example with turning a faucet to the right. So even though, as you can see, there's a large visual domain shift between the given video and the simulation environments, DVD allows the agent to complete the task in these unseen environments. The important takeaway is that training using human videos, shown in the purple and red bars, improves environment generalization significantly compared to only using robot data, which is shown in the green bars. And here we also find that DVD works on a real robot. So the first video here is the agent closing the door, but without having ever seen this toy kitchen set before doing training. And the second video, which is pushing the tissue box to the left, is without having seen any examples of this task of pushing things to the left during training. And so in summary, DVD is a simple and scalable approach to task specification that can leverage the diversity of these in the wild human videos to generalize to new environments and tasks. So the hope is that DVD inspires future work in applying broad data sets for more robust generalization capabilities. And there's a lot of really exciting directions for future work along this line. So first, our method focuses only on learning reward functions that generalize and doesn't actually learn a generalizable policy directly. Also, so far, we've only tested DVD on coarse tasks that don't require fine-grained manipulation. And lastly, the reward is non-Markovian. So, but it'd be interesting to explore using the reward to learn model-free policies with memory. And that's all I have. So thank you for listening, and feel free to reach out if you're curious to learn more about this.
Thank you, Amy. Thank you for the great presentation, and it's really cool to see having some works that apply data that goes beyond just robotic data. Really cool. In the interest of time, I'll ask students to ask questions in the chat, and we'll move to our next speaker, who is Igor Mordach, who's a research scientist at Google Brain as well. And he will tell us a little bit more about how we can actually simplify reinforcement learning formulation and maybe use some of the ideas that we know from large language models and supervised learning to do reinforcement learning better, reinforcement learning a little bit simpler. Take it away, Igor.
Yeah, thank you. So yeah, as Karol was saying, I'll be talking about treating reinforcement learning as sequence modeling. And by sequence modeling, colloquially, I mean combining, say, transformer-based architectures with large-scale pre-training. And I believe Colin a few weeks back already talked quite a bit about such models. So we are seeing a lot of research, compute, and infrastructure investment into this. And so it's worth asking, how can we, as practitioners in AI and robotics, get the most out of this investment? And so what we've tried to do is to frame the problem of making decisions, which would normally associate with reinforcement learning, as a sequence modeling problem. And by that, I mean not just using, say, transformer networks to model your policy or value functions, but actually replace reinforcement learning algorithms involving a lot of moving pieces, such as recursive Bellman updates, choices of discounts, factors, and so on. Replace all of that complexity with just a single sequence modeling objective. So this is a very drastic problem reduction, but I think it's worth asking, how far can just such a reduction take us? And this is the hypothesis that we try to explore in the recent decision transformer paper with colleagues at UC Berkeley. And so what we're going to be playing around with here is actually just the sequences, the nature of the sequences that we feed into these models. The choice that we've explored in the work is actually sequences of returns, followed by states, followed by actions. So these triples just repeated all over for across different time steps. And by returns here, I mean actually the sum of all the future rewards. So what this in essence can actually do is it can incorporate some hindsight information you have about the outcomes of this episode earlier on into the sequence, which ends up being very useful, as we'll see. So we take these tokens of return states and actions, feed them into a causal transformer model, such as, for example, what GPT models use. And we ask it to predict sequences of actions. And at a deployment time, we just autoregressively predict these action sequences conditioned on some target return, or maybe more broadly, some notion of optimality. So for example, we may ask that we've seen, there's some target score in a game that we know that we can get to, and we've seen that some demonstration data, this is in the offline RL setting, was able to achieve it. So we put that as target, and this idea actually goes back, has really interesting deep roots in optimal control and in inference land. So after doing all of this, the results are actually very promising in the offline RL regime, where we're seeing we've tested it on discrete control benchmarks such as a number of Atari games, continuous control like the OpenAI Gym environment, and these somewhat unorthodox key-to-door environment from DeepMind, which basically is really targeting long-term credit assignment, where I can only at the end of the episode open the door and get a reward if I have picked up the key much earlier on in the episode. So you really have to do the right thing in the beginning. And we're seeing that these models actually do, in cases, significantly better than behavioral cloning, and in some cases, kind of like about the same, or sometimes better, sometimes worse, than temperament difference learning approaches to offline RL. And there's actually some interesting things where, when these key-to-door environments, they attend to various very significant actions, like the attention weights in these models attend to significant events in the past. So I think I'll skip some of the investigations, but the idea here is not to try to introduce new algorithms or models, but it's really careful analysis and problem reduction to actually whittle down the space of possible methods and strive for simplicity and the ways to build on our community's efforts more effectively. So these are the links to the paper and the code if you're interested. And I think that's it for me.
Thank you so much, Igor. Thanks for the great talk. I'll also ask students to ask questions on the chat in the interest of time. And next we have with us Annie Xie, who will talk to us a little bit about how we can apply reinforcement learning to lifelong settings, where we can extend the period of an experiment, or where we can extend the lifetime of RL beyond a single experiment. Annie is a PhD student with Chelsea Finn. Annie, please take it away.
So I'm Annie, and today I'll be talking about some of our recent work on lifelong robot learning. So some of the current ways to learn multiple tasks are to learn each one from scratch, or to learn them together under the multitask learning framework. And in standard multitask learning, the agent needs to collect data in each new task. It needs to collect data in each new task round robin style. But this form of data collection isn't very practical for a lot of real robot setups. And so, for example, if you consider these two tasks, repeatedly switching between this block insertion and this bottle capping setup isn't very realistic. And what would be more natural instead are robots that can learn tasks in sequence. And that's just the lifelong learning problem. So a lot of the work in lifelong learning has been concerned with catastrophic forgetting, which evaluates how well an agent that's given a finite amount of memory and parameters can perform on previously solved tasks. And in this setup, we're kind of concerned about a different aspect of lifelong learning, which is forward transfer. Specifically, we allow the agent to retain all of its previous experiences, which isn't unreasonable if we consider the cost of storing data compared to the cost of collecting significantly more data. And so we also simplify the problem a bit by assuming that the state and action spaces are shared between tasks and vary across the different tasks. And the agent in our setup also only advances to the next task once it finishes learning the current one. So on this slide, we outline our solution to this problem, which basically alternates between an offline pre-training phase and an online improvement phase for every new task that comes in. And during the offline phase, we are essentially restoring the replay buffers from the earlier tasks and pre-training the agent on this data. Then during the online phase, we will improve the agent's policy with data that's collected online. And instead of just throwing away the prior experiences at this point, we can actually try to reuse them. But to account for like the differences in the data distribution, we reweigh the samples based on how likely they are under the current task versus an earlier one. And this ratio can be decomposed into these two highlighted terms here. The first term basically says, given a transition, how likely is this sample from the current task versus a previous one? And we can estimate this ratio with a binary classifier that's trained on the transitions. And we also transform this ratio by thresholding it. So we're essentially filtering out the irrelevant samples, and basically we don't have to actively use all the samples in the data set. And the second term that's underlined in yellow can be estimated with the size of the data sets. And what this term is basically saying is we're going to decrease the weight of prior samples as we collect more new samples in the current task. So next, we actually wanted to leverage the prior data even more specifically for exploration. Essentially, the intuition here is that prior experience on related tasks can inform the agent to which states to explore in future ones. For example, a robot that's doing tabletop manipulation generally needs to move its arm towards objects. And we build in this heuristic by appointing samples with states that were more likely in the earlier tasks than the current ones. And by doing so, the agent is incentivized to visit them more if they're useful. And then to evaluate our approach, we designed a family of key insertion tasks where we vary the placement of the box as well as whether they're placed flat or vertically. And we also varied the size and the orientation of the key. And for comparison, we looked at a few prior approaches that transfer learned weights, like progressive networks and continuous fine-tuning. We also looked at approaches that transfer prior data, like this method called JARC and standard off-policy RL. And overall, our method achieves the highest success rate across 3 different task sequences. And it even does better than if we were to learn each task from scratch. And then finally, we evaluated our algorithm on a Franco robot on a sequence of tasks that includes setups like bottle capping and block insertion. And to summarize, our method gets with 0.7 years of the goal, which is less than half compared to learning from scratch. Yeah, that's it. I guess there's no time for questions, but feel free to contact me.
Yeah, thank you so much, Amy. Yeah, we'll have questions on the chat, so if you could stick around a little bit, that would be great. Thank you. It's really cool to see that we can go beyond kind of removing all or collecting data only for one paper and then not getting back to this again. Very cool work. Thank you. And yes, I'll ask the students to ask the questions over chat in the interest of time. And I will switch over to presenting. All right, so we talked a little bit about how we can scale up data collection, how we can utilize broad offline data sources, including non-robotic data sources, and then how we can change the algorithms, reinforcement learning algorithms, to look more like supervised learning algorithms so that they can utilize more data. And then at the end, Annie also told us a little bit how we can apply reinforcement learning to lifelong settings. So there are a few takeaways that we could draw from this. We can scale up data collection by eliminating resets, and it's important also to keep in mind, as Archit pointed out in the chat, that actually by making reinforcement learning more autonomous, there's many more advantages than just scaling up data collection. And then there are multiple ways to broaden data sources via, for instance, incorporating non-robotic data such as human videos in the wild, or casting reinforcement learning into a simple problem formulation. And then we can also extend reinforcement learning to lifelong settings by retaining experiences. All right, so in the remaining, we don't have that much time. So I wanted to briefly tell you, in the remaining 2 minutes, let's say, I wanted to briefly tell you about some other open challenges that we haven't previously covered. And there's a few, although we covered a lot of ground. Generalization, where we assume that our meta-test distribution, meta-training distributions are the same, and it's very often not the case. So we also need to be able to generalize to out-of-distribution tasks, which is often the case with long-tail distributions. And I'll skip the details on that. We also need to look a little bit more into multimodality. So how can we learn priors from multiple modalities of data? So far, we've mostly looked at problems where the predominant modality was vision. There's many other modalities that, such as touch, for instance, that often are sound, that often have some additional complementary forms of information that we should be looking at as well. And then there are questions regarding the algorithm and model selection. So answering questions such as when will we know whether multitask or meta-learning is going to help, or how to select the best model based on the algorithm that we run. Then there's more work to be done in terms of benchmarks, although we are getting a little bit better at this. We want to have benchmarks that have sufficient breadth, that challenge current algorithms to find common structure. And then also benchmarks that are realistic, so that they can reflect real world problems that we actually care about. And we've seen some examples of that throughout the course, but I think there's more to be done there. And then there's some work to be done on improving the core algorithms themselves. So I think the theory for most of these methods is actually lagging behind quite a bit. So we need some additional work to develop a theoretical understanding of the performance of these algorithms. We can also look a little bit more into multi-step problems or lifelong learning problems where performing tasks in sequence present challenges. And as we've seen in the previous lecture on Monday, performing lifelong learning is actually can be quite difficult, and very often is understood in many different ways. So I think we could make a lot of progress here. And then there's probably many more challenges that you discovered in your homework and in the final projects. And since this is the last lecture, I wanted to briefly go back to the bigger picture. So at the beginning of the course, we talked about how machines are pretty good specialists. They can solve things such as Atari games, or playing Go, or even doing helicopter acrobatics. But they're pretty good in these narrow domains. However, when we look at humans, we are pretty good, what I would call generalists. And what I mean by generalist is that we have this ability to learn many different skills, build on prior knowledge to adapt to new environments, and have some sort of common sense. The ML systems that I showed previously, on the other hand, do not. So they're specialists that try to master a single task starting from scratch, disregarding a greater understanding of how the world works. And in this class, we took a step towards building machines that are generalists. There's a lot of topics that we covered that go in that direction, things such as how to learn multiple tasks with multitask learning, how to leverage prior experience when learning new things, for instance, with meta-learning, how to solve sequential decision problems with RL, how to learn general purpose models with model-based reinforcement learning, how to prepare for tasks before we even know what they are, such as what we did in skill discovery, how to perform tasks in sequence with hierarchical RL, and how to learn continuously. I think a lot of these things cover, we covered a number of things that can bring us closer to this goal of building generalist learning systems. But there's always a question, what else? What is missing? And I think that now you should be well equipped with the tools that you get to know in this class to figure it out. Thank you so much for being such an engaging group. It was a lot of fun teaching this quarter to all of you. Thank you also from the entire course staff, from our course coordinator, all the TAs, Chelsea, myself. Thank you. We'll see you.